All right, so that was an interesting experience. I recorded all the lessons that I'm going to post for this week and didn't realize that the microphone had automatically been shut off. So here I am re-recording everything for you guys, but in any case, it's okay. It's a little late, but better late than never, I guess. So we are starting our new unit. It is on equilibrium. It is probably the toughest unit of the year. So try and keep up with it. If you guys do have questions, send me an email. So here we go. Let's see if we can recognize equilibrium. So you guys have learned that the rate of any reaction depends on the concentrations of the reacting chemicals. So you guys know that the rate is equal to some constant K times the concentration of the reactants raised to some coefficient M. Uh, However, as a reaction does proceed in the forward direction, the concentration of the products increases and the concentrations of the reactants decreases. So as such, when these concentrations do change, so too do the rates. So you guys are familiar that our rate law expression is based on the concentration of the reacting particles. And so uh, as this happens, and as you proceed in a chemical reaction, the rate of the forward reaction begins to decrease as time goes on because I have fewer and fewer particles because they're being converted into products. And the opposite is true for products. We actually have to look at reactions as being viewed in both directions. So it's not just reactants turn into products. Products can also turn into reactants. And so as a result, at the beginning of the reaction, of course, our products have a reaction rate of 0 going in the reverse direction because I don't have any yet. But as this reaction goes forward, I get more and more and more products being formed. And that means the rate in which the reverse reaction is going is faster and faster and faster. So what is equilibrium? Well, equilibrium, or you reach an equilibrium when the forward reactions rate and the reverse reactions rate are equal to one another. When they are equal to one another, we reach a state of equilibrium. That has nothing to do with the fact that I have equal concentrations. I'm talking about the rates of the reactions. So let's take a look at some examples of this. So for example, sugar dissolving into water. If I take a 1 spoon of sugar or maybe Kool-Aid, because I remember doing this when I was a kid. If I take a spoonful of Kool-Aid and I drop it into a large container of water, you'll notice that the Kool-Aid dissolves very quickly and you don't have any more solid product left or solid material left. It's all dissolved in. As a result of us having that happen, if I continue to add more and more Kool-Aid into the water, you'll notice that at some point it reaches a point where you've got like a film almost at the bottom of solid material that's not dissolving. Now, at that point, you've reached the saturation point of your solution. In other words, I can't dissolve anymore. But that doesn't mean that the dissolution has stopped. In fact, it hasn't stopped. What you end up seeing is the rate at which these chemicals, this Kool-Aid, is dissolving into the water is equal to the rate at which it's precipitating out into its solid form. So the reaction rates are equal. It has nothing to do with the concentrations being equal. It has to do with the rates. So how quickly it's dissolving versus how quickly it's precipitating has now become equal at that point. And that's why you see a fixed amount of Kool-Aid sitting on the bottom. It's not as though the Kool-Aid amount that's sitting on the bottom is growing, and it's certainly not as though you run into a situation where it's going to start to dissolve, because if it's dissolving, that means you haven't reached that point, and you haven't reached that equilibrium there. Another good example is water in a closed container. So water in a closed container, if I take a bottle of water and I put it on my desk and I let it sit there, a year later I can come back. That water will still be there because it's in a closed system, but there is an equilibrium there. The equilibrium exists between water in its liquid state and water in its vapor state. Where's the vapor? Well, there's air in the bottle. And so if there's air in the bottle, part of that air has water vapor in it. And you guys have probably experienced this with leaving water bottles in your car at nighttime, depending on whether it's hot or cold out. So let's think about it this way. You take a bottle of water, you drink half of it, let's say it's at room temperature, you go inside and let's say it's, I don't know, early December. So it's not quite cold enough outside to freeze, but it's cold enough that in the morning you're going to have some nice cold water in your car. What's the first thing you notice? Well, when I get into my car, I look at the water bottle. The water bottle has depressed. It's been squished down. Well, why has it been squished down? And the reason is because as I change the temperature, I change the rates of the reactions there. Now, the reaction that I have there is the rate the rate at which water is going from liquid state to vapor state, and the rate at which it's going from vapor state to liquid state. If the temperature starts going down, water is going to start to condense much more easier, and so the water is going to leave the vapor state to go into the liquid state. Well, if it leaves the vapor state, that means the pressure inside the bottle is going to decrease. And so you see the bottle actually squishing down. And so the atmosphere actually pushing down the bottle. Or the same thing you might also see in the summertime, right? You take a half-drank bottle of water that's room temperature, leave it in the car, you come back, you'll notice that the bottle seems like it's puffed out a little bit and that there's bubbles inside the water. Well, why is that? Well, when you increase the temperature, you're increasing the rate at which a water molecule would go from a liquid state to a vapor state. So if I'm increasing that, it means I have more vapor, and that means I have a higher pressure, and the bottle looks like it's puffed outwards. Both of these situations have been, that I've talked to you about, are physical processes. We're not only interested in physical processes, we're also interested in chemical processes, and we're going to talk a lot about this the rest of the course. So I'm not going to give you guys specific examples of these chemical ones, but understand that we actually have two different types of equilibria that can be reached. We have homogeneous equilibria, which is equilibria where everything is in the same state. So, a gas reacts with another gas to produce a third gas. All of those are in the same state, so we have a homogeneous equilibrium there. Of course, and then it'll lie somewhere in between them with some products and some reactants present. Or you can have a heterogeneous equilibrium where you have two things reacting together and they change state. So a good example of this is two aqueous solutions producing a solid precipitate. You reach an equilibrium. We're going to look at that more in detail a little bit later when we look at KSP. Finally, there are 4 conditions that apply, and you must satisfy all 4 of these conditions in order for a system to be considered to be at equilibrium, or to even reach equilibrium. So condition number 1 says that equilibrium is achieved in a reversible process where opposing changes are equal. So the first example there, H2O liquid going to H2O gas, is exactly what I was just talking about. So we're talking about the rate at which it goes from liquid to gas, and the rate at which it goes from gas to liquid is equal if we're at equilibrium. The second one is that first one's a physical process. The second one, of course, is a chemical process where I have some H2 reacting with some Cl2 to produce 2 HCl's. So that's a chemical process there, and so you reach an equilibrium when the rate at which H2 and Cl2 are reacting in the forward rate, which is equal to the rate in which HCl is being turned into H2 and Cl2. When the rates are equal, we reach our equilibrium. Number 2 says that the observable properties do not change and they must remain constant. If I'm watching a chemical reaction happening, and let's say I'm looking at color, for example, and the color is continually changing, it means there's more chemical reaction happening at a rate that is faster than the reverse rate. So, let's say we have a chemical reaction going on, and that chemical reaction produces a red color. If you see the color turning deeper and deeper and deeper red, it means that the rate of the forward reaction, which is producing that red color, is still faster than the reverse reaction. When that color change stops, that's when you reach an equilibrium, because then the rate at which it's producing is equal to the rate at which it's decomposing, and so you end up in a situation where you have an equilibrium achieved there. Pressure is another good example of this, right? So if the pressure in a system is changing, it means I'm producing more or less of a gas or multiple gases. And so if I'm producing more or less of them, then I haven't reached that equilibrium yet. You reach that equilibrium when when everything remains constant. The third one is that equilibrium must occur in a closed system. If you don't have a closed system, then things can escape or come into the system, and if you have things escaping or coming into the system, then you could never reach an equilibrium because things will continually change and they'll never be able to have that constant piece there. So constant pressure, constant temperature, constant number of molecules has to be present in order to have a system at equilibrium. And then the last one is that equilibrium can be approached from either direction. So let's say I have x plus y goes to z. If I start with only x and y, it will produce z until it reaches that equilibrium. if I start with only Z, it will produce X and Y until that same equilibrium in the same proportions is reached as well. So, for example, the proportions of water vapor and liquid water are the same at equilibrium regardless of whether you start with water or start with liquid water vapor or liquid water. Okay, so that's pretty much it. That's just your introduction to equilibrium. Watch the other demo video of the guy that has the containers with a blue fluid. It does really help you visualize equilibrium there. If you have any questions, send me an email. Thanks, guys.